Hi friends, thank you for clicking. The story I prepared this week, I promise you won't regret joining today. I'm going to show you a complete printing project with the Sovo SVO8. It will cover all aspects from fine-tuning a special purpose filament in Orca Slicer to all the preprint considerations in the slicer and share the experiences gathered while printing something quite large. In fact, the piece we are printing would have been impossible on any of my other machines, which are all limited to a 300 by 300 millimeter build area. This is Gergo, and you're watching Gergo Print 3D, the YouTube channel about my 3D printing adventures and all kinds of DIY projects. Like all my videos, this one also includes high-quality subtitles, which translate well into other languages too. I recommend turning them on. So, the part we are printing is an air intake vent for a race car being developed by a group of students at the Technical University of Budapest, my alma mater. The 3D printed piece itself is not going to be used directly, but will serve as a mold for carbon fiber lamination. Given the specific strength requirements, they have provided the material for printing, the tough UltraFuse PLA Pro 1 filament from BASF. We started by creating a filament preset based on my own take on Sovo's PLA settings and updated these according to the speed, cooling, and temperature recommendations in the general column on this spec sheet that came with the filament. But then we utilized Orca Slicer's calibration tools to fine-tune these settings on the SVO8 to find the optimal temperature, flow rate, pressure advance, and max volumetric flow rate for the best outcome. All these tools can be found in Orca's calibration menu. If you already know how to use these, you're welcome to skip ahead to the next main chapter, but I might have some extra tips, or you might have alternative suggestions. I encourage you to share them with the community in the comments below. We choose the calibration test we want to run, and it's basically best to follow them sequentially. For the temperature tower, we input the range suggested on the box, 200 to 230 Celsius. Then we send the model to the printer. It takes about 30 minutes to print, but you can make it quicker by choosing a shorter temperature range. Each section is printed at a different temperature. This filament is top-notch. It performs well at all tested temperatures. The overhangs look the cleanest at 215 to 220. So for stronger layer adhesion, we pick the higher. Let's enter and use it already for the next test, which will help us tune the flow rate. Nothing to configure here. It just gives us the model, which we print. 2 layers to watch carefully, the first and the last. Of course, you'll need to have your Z offset dialed in perfectly. In the first layer, we are looking for nicely connected lines, no gaps and no overlapping. Black filament is a bit hard to see, but this one here, you can see it's way under extruded, and these in the top row are the other extreme. For the first layer, 0, -5, and -10 all look okay to me. Then we should look at the tops, the last layers printed. Which one of these look the smoothest? Even 0 has some ridges, a sign of slight over-extrusion. I think -5 is the safest pick here. The correct flow rate is probably between -5 and -10%. We could do a second pass with finer differences between the pieces, but I'll just use this -5, which means we take 5% from the 100%, which corresponds to a factor of 0.95. we multiply the current flow rate of 0.98 by this 0.95. Now, don't enter the formula here. Would be nice if we could. I just use this box to explain how we got to the 0.931, which I leave as a flow rate for this filament. We can save and move on to linear advanced tuning, which is not really relevant to this model since it affects how sharp corners are printed. And this part has none of those. But let's still do it for your benefit. This time I keep the default parameters, linear advanced controls, the flow rate near the corners. On the bottom of this test object, flow is not reduced near the corners, so we'll see a bit of bulging there, and even the seam line will have little blobs due to too much filament at these critical points. Linear advance is increased as we get higher in the model, to the point where it becomes so prominent that the corners thin out and the seam disconnects. When analyzing the result, we pick an optimal point where the corners look the sharpest and the seam line in the back is still connected. This point is 25 millimeters away from the bottom for this given filament, so I just multiply the default step of 0.002 by the 25 millimeters and get the pressure advance of 0.0513. Again, don't put the formula there. I just use the box to explain how we got the value. Next up is retraction tuning to minimize stringing. It controls how the filament is pulled back or retracted into the nozzle during travel moves. Again, not so important for this particular part, where most of the layers are just one continuous line. There is no jumping around except for the support trees, but there we don't really worry about aesthetics. Let's still do it for the educational value. The default retraction distance of the SVO8 is 0.8 millimeters. So let's set the test to run from 0 to 1.5, about double of the default value. We are looking for stringing. Again, this filament and the SVO8's stock extruder are both so good that we see almost no stringing, except at the very bottom of the columns. The notches are for each step of 0.05 millimeter increase in retraction distance, as we have set it. We can see no stringing above the third notch, which theoretically corresponds to a retraction distance of 0.15 millimeters, which would suffice for this filament, but I will just leave it at its default for this project. The last calibration test we will do is for maximum volumetric speed. How much filament the nozzle can push out per second. This is most important for fast printing of large objects, where the motion system could be moving the hot end faster than it can get filament out. This is a large model, but we are not going to print it at the highest possible speed to achieve stronger layer adhesion. So, flow rate will not really be a limiting factor here, but I'm still curious what this filament is capable of. Being PLA, I'm sure it will be fine at 10 millimeter cube per second, and just out of curiosity, we can aim at 40. We'll stop printing the test object where it fails anyway. And to speed things up, I'll set the step to 1. This test object has long, straight lines where the tool head can reach the speeds that really test the flow rate. It goes faster and faster the higher we get, and we are looking for the last good layer. We could inspect and measure after printing with a veneer caliper, but if you're using my macro pack, I've added a current Z option in the tune menu, which is available during printing. According to this, we can see the first gaps in the lines at 12.9 millimeters. So a safe value would be at 11 millimeters. Since the test started at 10 millimeters cubed per second, we can enter the value of 21 in our filament settings. Equipped with the fine-tuned filament preset, we were ready to slice. As you can see, the part barely fits the build area of the SV08. In earlier prints, I had slight first layer issues on the left and right edges of the print bed. Given the option, we oriented the part as much away from these edges as possible. I'm not sure why, but they've asked for extreme strength for the whole object. So we followed their request of 3 mm wall thickness. Ideally, this would be a job for a 0.6 or even a 0.8 mm nozzle, but I haven't yet received the large nozzle kit from Sovo. So we set the stock 0.4 mm nozzle to print 8 perimeter loops and 12 top-bottom layers at 0.25 layer height. But kept the infill density fairly low for most of the model. They specifically requested this bottom slate area to have 100% material density, which we were able to set using a modifier cube. See, I right-click on the object and select Add Modifier Cube. Then resize and overlap this yellow cube with the base of the object. Now we can switch to per object settings in the process section and make adjustments in the settings for the overlapping parts. We just set infill to 100%. With such large and dense bottom layer, I was concerned about warping. This thing will pull on the bed like crazy. As you will see, this concern of mine was not baseless. The corners of the bottom are all rounded, which helps to avoid curling up, but we have also added as much brim as could fit on the build plate. Still, this curved section here on the left will need supports. We enabled 3 supports and set the threshold to 25 degrees until we saw the optimal amount of supports. Notice in the preview, the global brim setting did not affect the 3 trunks. And without giving anything away, let's just say we'll circle back to this, and not even just figuratively. Mark my words. Following the recommendations for the filament, we slowed down the wall and infill printing speeds, and with everything prepared as best as we could, we sent the print job to the printer. First layer printed okay, though it needed a little bit of Z height adjustment. See, halfway printing the first layer, I heard a cracking noise, and the first layer lines on the right side started to look too squished. The bed must have warped up just a tiny bit because of heat expansion and the pulling force of the first layer. I just raised the nozzle by a few hundredths of a millimeter to allow more space from the bed's surface. It wasn't a good idea, though not apparent immediately. Another annoyance was with the filament holder. The design aimed at reducing friction with bearings indeed facilitates the feeding of sensitive flexible filaments. However, the narrower 750 gram plastic BASF spools tended to unravel, particularly when full. I resorted to an empty toilet paper roll and a Sharpie as a makeshift solution, though this issue needs to be addressed later, maybe by adding some kind of a variable friction clutch control somehow. Comment below if you have any suggestions. Subsequent layers printed beautifully, though at 100% infill, the filament has nowhere to expand. Even though we did flow tuning earlier, I had to further reduce the flow rate on the fly to stop the nozzle scraping the previous layers printed. This fixed the scraping, but it took a long time. 5 hours into the print, and we were still printing this solid base, still under 10 millimeters, though it all seemed to go according to plan. And then the problems started. I couldn't check on the print in the next 2-3 hours, and by the time I looked at it again, the front left corner started to lift. Remember how I increased the Z height by a tiny bit to balance out the warping of the bed while printing the first layer? Although it fixed the side where the bed slightly lifted, but of course caused a bed adhesion issue on the other left front side of the bed. Close to 8 hours into the 18-hour sprint, we decided not to cancel, since the warping did not affect the main part of the object, only the base that is going to be clamped down. So we let it continue, hoping the rest of the base will hold it to the print bed well enough. It did, except 10 hours into the job, another catastrophic incident happened. A row of supports became loose and got totally displaced. This was unrecoverable. Although we set a fairly large brim for the whole project, turns out that setting doesn't affect supports. For supports, we need to configure brims separately, and it's not even called brims there. I'll show you in a minute because we had to cancel at this point. We wasted some time and a lot of filament, but gained much experience, and we still had enough filament, though a different color, for a second take. So here are the settings we changed for round 2. First of all, we increased the brims around the base of the tree supports using the setting first layer expansion. Yes, that's how it's called. That was a costly oversight in the first take. Second, we reduced the infill density of the base from the unrealistic 100% to just 25%, which is still significant, and at the same time increased the number of wall perimeters in this part of the model to a whopping 12 to keep the strength. We also increased the Z-hop distance slightly from 0.2 to 0.25, just to make sure the nozzle wouldn't touch the printed surface in travel moves. Not a setting, but I re-cleaned the PEI surface, wiping it multiple times with isopropyl alcohol. And most importantly, I let the bed heat soak even longer, a full 15 minutes before starting the print with the adaptive mesh scan. This heat soaking macro is also part of the little collection I made available on CALDS3D. It will heat the bed to a selected temperature and move the inductive probe close to the bed so it too gets acclimated. Not related to the problems, but we also rotated the model 180 degrees to have the more interesting supported curved side face the time-lapse camera. These small changes eventually brought success. After another full day of printing, no intervention was necessary. The print completed without a hitch. Perfect success. The part is now ready for the carbon fiber lamination process and will be part of the race car that is going to be rolled out in a week or 2. I've shown you the whole process now, with its ups and downs to help you with big print jobs. That's where the Sovol SV08 really shines, in my opinion. Whether it's parts for a race car or a big statue or helmet, I hope these tips on filament tuning and settings will help you succeed with your Sovol SV08 or any 3D printer you use. Stay tuned, because there is a lot more in preparation. We'll take a look at the new official filament presets and how we can improve Sovol's preprint macros. I'm also in the process of upgrading my SVU 6 Plus with something similar to what we've done with the T300 recently. And I'm still busy learning more about laser cutting and engraving. By the way, please show some love to this last video about the MacPow X5. And all my SVU 8 videos are also at your disposal. Otherwise, you know our routine. Let's go print 3D. Thank you for all your likes, comments, and subscriptions in support of Gergo Print 3D.